Well, it's not I mean, GPUs, NVIDIA right now is the most valuable semiconductor company by far, much larger than all the other ones. And the reason is because they make GPUs and sell GPUs, and everyone wants to buy all their GPUs. So we know how to do the training in the cloud. It just costs a lot of money. In some sense, yes, maybe that's a little bit of an open problem as well. One big problem with the way we do it nowadays is that it really stresses national budgets. It stresses the electrical grid. So right now, you may have heard this. If you haven't, maybe you will be surprised. All the big companies, Microsoft, Google, Amazon, they are seriously not only talking about, they are going to build their compute systems with a mini nuclear reactor attached to it. And the reason is that the growth, and again, everyone is worried about global warming and all these things. At the same time, I think I've read somewhere that 25% of the electric consumption in Ireland, which is not a small, I mean, it's a small country, but it's not an insignificant country. 25% of their electricity is taken by the fact that all these companies have massive data centers there. So yeah, it's a big problem in that sense. But that's a problem that can be solved with a lot of money and nuclear reactors and things like that. On the other hand, having a self-driving car, there are some other limits. You cannot have a nuclear reactor. So that's why I'm saying at the edge, training is an open problem in the sense that we don't know how to do it really in a meaningful way. Yeah. Other questions? Okay. Yeah. Is there? Okay. So let's get to more recent times. So the snake has become faster and faster, and in the last few years we've had kind of amazing things. Yes.
CPUs could be done more perfectly using concurrent programming. So if we talk about training more efficiently in GPUs, would that be more efficient if we use the machine learning code or algorithms in form of?
Well, so I don't agree with your premise. Your premise is that CPUs are somehow
and then coming to how the CPU core increase.
Yeah, but that's not even close to being enough. So in some sense, you can think of the GPUs being the next step to what you describe. So you're right that we started with single core CPUs, then we went to multi-core and Moore's law and all that. You can think of it, if you want to think in terms of that, yes, GPUs are the next step. Whereas in a multi-core, you maybe have 16, 32, maybe 64. What do you mean you are not utilizing them? You are utilizing them. You mean GPUs? You are utilizing it all.
If I see a 4-core CPU, and if I'm writing a program which is not concurrent in features, at a time, one core will only work, other three will be idle.
Yeah. So we'll talk about that. That's not how GPUs work. So GPUs are massively parallel. We are going to talk about that. Yes, you're absolutely right. Everything, but that's already done. So all these thousands of GPUs that need a nuclear reactor, trust me, they all work in parallel all the time. That's why they need a nuclear reactor. If it was just one, yeah, you would need a cup of chai. Yeah, no, so that's already taken care of. Okay, so yeah, so basically this is the kind of the thing that really started it all. The thing that started it all are really deep neural networks. So instead of having, you know, one or two hidden layers, now you have multiple. And the first one didn't have that many. You know, it had maybe 4 hidden layers, but it really showed the importance, and this is for the hardware. I mean, again, this is an architecture that's still kind of implemented as a program in software, but you know, it really is hardware, and you know, there are many nowadays. There are many hardware implementations of this. At the time, this was not even a GPU. This was just a CPU. It was, yeah, I don't have the year there, unfortunately. Yeah, so 1996, I think, or 1998. So this is a long time ago. But you know, this was kind of the first modern application of AI concepts. Again, the AI concepts, you know, go back many decades, and it was this benchmark called MNIST, which had a very practical application. So the practical application is what? What do you think? No. Look what it's doing. It's recognizing digits. Yeah, this is for banking. Yeah, exactly. This is for banking. So, you know, the bankers really wanted to, you know, get rid of some humans that were reading checks by, you know, with their eyes and do something like this. So they, you know, and yeah, these are all kinds of, you know, digits, numerals that were being used. What made it, you know, really important was this concept. So, and again, this is another way to think about hardware. The original perceptrons were what's called fully connected. So all the inputs were connected to all the neurons, and then all the neurons in a layer were connected to all the neurons in the next layer. So that gives you the most flexibility. Unfortunately, it's not very scalable because, you know, at every new layer, you have another times n, times n, times n. So very quickly, you have a lot of weights and a lot of wires, so to speak, if you want to implement it in hardware. So this concept of a convolutional neural network was an application-specific refinement of the fully connected. And the idea was that, and you know, this is also, you can think of it as biologically inspired because there is some evidence that our eyes and our visual system works that way. Clearly, when you want to recognize one of these digits, you don't need to, you know, somewhere there to basically have inputs from both corners of that digit. Everything is kind of local, right? So you want to detect edges and you want to detect something like that. So basically, again, the idea was that you have what's called a kernel or an image patch. So this was the image of the digit. And then instead of connecting all these inputs to all the neurons in the next layer, you can think that you have specific neurons, one neuron that only looks at this region, another neuron that only looks at this region, another neuron that only looks at this region, and another neuron here. And basically, then this is going to be the kernel. And here we are getting to the question about matrices and all that. But basically, you are applying this kernel, and applying basically means you multiply the input times the weight, and you sum it together, and you get some number, okay? So it's still the same network that we had before. The difference is that we have basically fewer inputs that are connected to the neuron, and that's a big advantage in terms of computational load. And again, this is how that network looked like, and you can see it's already much more complicated. And right now, you really need to think in terms of matrices and all that. But I want everyone, because again, we are hardware guys. Well, not everyone, but from a hardware perspective, even if you use matrices, fundamentally it's still the same input times weight and add and all that. So you have multiple feature maps at each layer, and feature, I'll talk a little bit about what that means, but you can think of feature is recognizing a specific feature, again, a specific aspect of the image. And you have all these convolutional neural network layers. And then at the end, you still have fully connected network. And the reason is that, so maybe let's see, I think if we, I'll explain a little bit later. But basically, this is the advantage. And, just this figure should convince you that this is a good idea if it works well. If it works well, so if it works well, it's clear that this is a fully connected layer network. This is a convolutional network in which you have fewer connections. You can very easily see the advantage in terms of simplicity of computation and hardware. Here is where we go from CPUs to GPUs. So really, and again, this is another reason to say, why should we think about AI hardware? Well, because AI hardware would not have been possible, AI would not have been possible without hardware. It's kind of interesting that, GPUs have become so important because everyone knows that GPUs were really invented for games. That's it. So thank you to all the gamers for basically pushing the technology, the computer people to, serve your needs to, shoot rockets in the sky and allow this. So at the beginning, again, GPUs were very special purpose, just for games, just for images. But then some academics, and even at my university, I collaborated with someone that now is at NVIDIA and has been at NVIDIA since then, who started not for AI, but for scientific computation. Again, weather, all these things, they need a lot of compute, and it's very similar, actually. It's still differential equations that you solve. So again, academics have thought, how can we use these wonderful hardware machines to do, matrix multiplies? And again, they came up with this concept of general purpose GPU. So again, we weren't to that. But basically, once GPUs became available for AI, immediately you could take these deep neural networks and make them even deeper and even wider. And you can see that, this is, this is AlexNet, and this really revolutionized, this is really the start of the AI revolution, because it was able to beat all the humanly designed algorithms by a lot, just by doing basically backpropagation and training. And there were, a few new features that were added, and we'll talk about these pooling and all that. But fundamentally, it's one of these neural networks. Okay, so now let's talk about these matrices that we had some questions about. Again, this is the fundamental computation, but you can very easily set this up as a vector matrix multiply and do the computation like that. So this is going to come over and over, during the 5 days of this week. The fundamental operation of AI is multiply, accumulate. You just multiply and add, multiply and add, multiply and add. And for those of you that have taken DSP courses, you know that max are, so it's, and like I said, for any of the weather, the scientific computation, they're all multiply and add. So there is something fundamental about multiply and add. But at the end of the day, to have a successful AI hardware system, you just need to do a lot of multiply and adds as fast as you can. And I don't want, I'm wondering, so we need to talk about that, but let me go a little bit more. So when you do this on a CPU, because we had a discussion about the CPU, you can basically set this up in some sense as a, when you do a vector matrix multiply, you basically can set this up as a nested for loop where, again, you have all these indices of the, so you have an input activation that's M times K. And by the way, I'm going to share all these slides with you. So you can take notes, but don't, you don't need to go too crazy with the notes. And then you basically have a weight matrix and you multiply, the way you usually multiply matrices, and you have an output activation matrix at the end. And that's it. This is the main computation. And the only thing is that you have a gazillion of them. And again, to do, the previous discussion, the only way to really make this very, somewhat fast is to use a lot of parallelism. You cannot do this, on a simple CPU one by one. So this brings us to, and again, I'm not sure how many of, again, I apologize for people that already know this, but I think these are important concepts. So when you talk about parallelism, you kind of several types of parallelism. And the, Flynn came up with this taxonomy many decades ago. But basically, you have the conventional, computer, single instruction, single data means, you fetch an instruction, you fetch your operands, you do the operation, then you write the result, and then you go to the next instruction, single instruction, single data at a time. And then the kind of the multi-core CPU does something that's called multiple instruction, multiple data, where fundamentally each processor can run its own program, its own thread, with its own data, and you have, some place where the instructions are coming from. There is this concept that's really not that useful. There are not many examples of useful, but an important one is this single instruction, multiple data, where you take, an instruction and you fetch an instruction, and then instead of fetching just one data at a time and do the operation, you fetch multiple data at a time and you operate on all of them in parallel. So, and I think that's the discussion about CPUs and GPUs. With the CPU, you can do this, okay? With the, GPUs don't do exactly SIMD. They do something called single instruction, multiple thread. But anyhow, you can think of it, it's like SIMD. So which one is more powerful? MIMD is more powerful, but what's the disadvantage? Power, well, before we get to power. Yeah, I mean, it's much more complex, right? So you have more wires, you have more stuff. So if you really want massive parallelism, and if you can, again, it's like with the CNNs, if you can do as well here as here, then, by doing this, you get, for the same area, you get much more parallelism, or for the same computation, you get less area or, less power. So that's really why people are using this. For the type of compute, so that's the advantage of AI. The programs are incredibly simple. You just multiply numbers over and over and over and over. You don't need a complex system to do that. So that's why this is the winning thing. So, and this is a little bit more along the same lines, CPUs versus GPUs. You can see, and this is not a very modern CPU, it's a relatively old CPU, but you can see it has a lot of stuff, out of order execution, many levels of cache, control, all kinds of things, just so that, you can get slightly faster thing. And again, if you look at it from an area perspective, this is, how you can have a floor plan for a kind of a CPU, a lot of control. So that's the important part. This control takes a lot, branch prediction, all kinds of caches. On the other hand, the GPU is all green, just ALUs. So that's why GPUs are really winning this race, because they spend most of the area on what's really important, which is, at the end of the day, we just care about those multiply and adds. Yeah.
I have a question about that branch prediction now.
Sure.
Right to the previous slide, to the nested for loop data flow, I see a lot of for loops there.
Yeah.
Do you still need some kind of branch prediction?
No, all those for loops are so deterministic. There is no branch prediction. You know exactly. So if you look at hardware for AI, not GPUs, we'll talk about those next day or two. Accelerators. For these for loops, you don't need any control. You just need a counter. You can implement this with a counter, where you just count and then goes back, and there is no branch prediction you need when you have if then else's, and when you have uncertainty about the branch. This one is very deterministic. There is no non-determinism here. Yeah. You have branching in some sense, but you can do it with a counter. Other questions? Okay. Yeah, so another important concept. So I talked about Flint's taxonomy. Another important concept is what's called Amdahl's law. And Amdahl's law is trying to look at the speed up that you get when you use a parallel architecture. And the ideal speed up, if I have n cores, is n, right? So that's what I would hope to have. The issue is that any application, even the most parallel ones, still have some level of sequential execution, where you need to set things up, you need to do some things. And that aspect of sequential is going to limit your speed up. And there is this very simple formula, again, coming from Amdahl. Amdahl, by the way, I worked, I'm pretty sure, at kind of the first supercomputer company in the world called Cray Supercomputer. And that's where basically they kind of figured this out. But here, and this might come as a surprise to some of you. I mean, to me, it was a little bit surprising when I when I saw this. So let's say you have on the x-axis, the number of processors. And, it's everything from one processor all the way to 64K, 65,000, whatever. And here you have the speedups that are available depending on the level of parallelism. And the level of parallelism is represented as a percentage. If your level of parallelism is half, half of your program is parallelizable, the other half is not, the maximum speedup is 2, okay? So, but what's interesting that even if your level of parallelism is 95%, which sounds like a lot, right? Your maximum speedup is 20. So you really need to pay attention to these things when you have this opportunity for a lot of parallelism. But again, you kind of need to be aware of it. Another important concept, and those of you that were at the VLSI conference, you've heard me talk a little bit about this, is this concept of a memory wall. And again, that's a very hardware kind of thing where, and this has this, there is this name of von Neumann bottleneck. So von Neumann, basically, when he came up with this concept of a computer, again, in the 40s, basically, and again, in retrospect, I'm not sure that this, if you look at how we operate, right, like our brain and all that, we don't have this separation. But somehow, we are still stuck with this concept. We still have this division of processing and memory. And the processor always goes to memory, gets an instruction, then gets data, puts it back in memory. And, the more the processor has become faster and faster and more parallel, and the more, the memory and, all these AI, applications that have all these gazillions of data, this has become more and more of a problem, this memory wall. And, like, for example, you need basically 1 terabyte of storage for all the weights of a GPT-4 type. So, 1 terabyte of storage to go back and forth every time, it's a problem. So, again, this has been an issue for a long time. So again, the computer architects have come up with this hierarchy of memory. Again, the first computers in von Neumann time, they literally had just one memory. That was it. You always would go to memory. Nowadays, it's much more complicated than that. We have this memory hierarchy, all the way to disk storage and, main memory and, multiple levels of cache, 1, 2, 3, and the register file. So this has really alleviated the problem of the the memory wall. But again, the solutions to deal with this memory wall at the system level for large systems have led to some interesting things. And again, there are trade-offs. Engineering is all about trade-offs. So if we have a bunch of CPUs and a bunch of memories, ideally you would want every CPU to be able to go to any bank of memory with the same latency, the same throughput and all that. But you can see the issue then, you have this relatively complex connectivity that you need to take care of. On the other hand, if you have a CPU with associated memory kind of local, then the advantage is that you have much simpler kind of connectivity. On the other hand, you are going to be much faster going to your local memory than to the other one. And these have these names: uniform memory access and non-uniform memory access. So this is uniform memory access, this is non-uniform. And again, from a hardware perspective, these are very important concepts. So one way to break the memory wall is to basically move your processing into the memory block itself. So that way you have, and again, it's an extreme case of this non-uniform memory access, because then this processing only has access to that data. So you need to make sure that the data is in the right place. But this PIM, or processing in memory concept, is an important one. Okay, so how are we doing? So again, what's the schedule for the students to not starve and whatever? Okay. So I'll try to wrap up by 1 then. Okay. So until now, we only talked about these feed-forward neural networks, in which basically the the connections are from input to the next layer to the next layer. You can notice there is no feedback. There is no there are some short circuits, I should mention, with some of them, but fundamentally it's it's a very feed forward. And something that you can notice is that from the point of view of hardware, digital hardware, in digital hardware we have basically 2 types of circuits. We have combinational circuits and sequential, right? So the sequential ones, you have state. You have registers, you can memorize things from the past and reuse them and things like that. So all the networks until now were purely combinational. So for some applications, you definitely need or want to have some kind of a state. You need to, the simple example is language, right? So in order to for me to be able to say all these words one after the other without sounding gibberish, I kind of need to, when I'm saying the next word, I need to know what I was saying until then, and, to have. So that's where this concept of a recurrent neural network came. Again, the idea is relatively simple. It's exactly the same as in digital circuits. How do we create a sequential circuit from a combinational one? We put a feedback, right? So that's how you get a latch from a gate. So same thing here. Instead of having just feed forward, now you have some connections that go backwards. And I'm not going to spend a lot of time here. Again, just to go from this fully connected to, yeah. I think I have some slides here out of order. Yeah, I apologize for this. I'm not sure how this happened. Once you have these recurrent neural networks, though, so yeah, so this is the justification. So I'll take out those 2 slides. They were out of order there. The idea is that when you have images, you don't really have the need for this sequentiality. But when you have some kind of a time series like language or something else, you need this temporal order. And that's where you have this memory state. So one problem with this is training. And again, we are not going to spend time on that. But training these things has been very tricky, because fundamentally you end up to train them in backpropagation. We don't have the concept of time. So in order to train one of these recurrent neural networks, you need to kind of instantiate it in time. You can that's called unrolling in time. So at every time step, you kind of create a new layer in the network, and then you can train. The problem is that for long sequences, you have really deep networks, and that leads, when you try to do that chain derivative, you get what's called this vanishing gradient. So then, and again, we are just going to talk about this for a few minutes. But basically, people have started to bring more complex concepts in the neural network. And here you can see one of these examples. This is called long short-term memory. And again, the idea is that the designers of this have tried to come up with ways to deal with with these unintended things that happen with recurrent neural networks. So one thing that happens, for example, is that when you have something happening at the beginning of the sequence, by the time you get to the end of the sequence, the effect of that thing at the beginning is very little. So that's a long-term memory kind of thing. So again, they came up with complicated things inside each. So instead of having just a simple neuron, you have some, state kind of things, and each of them with their weight. So this was not very impactful at the time, but it turned out to be very impactful by the way they set up the problem, because the way they set up the problem was really the precursor to what we do now with GPT and ChatGPT and things like that. And here is the example. And again, this is before ChatGPT and things like that. But they were looking with these recurrent neural networks, they were looking at applications to language. And some typical applications for language are translation. So basically, you have some kind of inputs in one language, and maybe you have the outputs in a different language. Another example is basically, for example, what's called sentiment analysis. So this is something that the internet companies are very interested in. If you have a movie on Netflix, they want to figure out, Netflix trying to figure out if people like that movie or don't like that movie. And the way they do that, they go to the reviews of the movie and try to figure out, is this review positive, negative, neutral? Are they angry or happy or whatever? So that's an example where the input is a review, and the output is some kind of judgment, good, bad, neutral, whatever. Another example is when you have just one input and the output is a sequence. And again, that would be some kind of generating, this one input could be a prompt, and the output could be, a story. And they also came up with this concept of encoder and decoder. And again, in translation, if you think about trying to do translation this way, it most of the time is not going to work, because why wouldn't it work this way? There's a very simple reason. So think about these, they are words in a sentence. The order changes in different languages, right? So if in some language, you start with a noun and then verb, whatever, and here it's verb, noun, it's not going to work. On the other hand, something like this, where you take in one language and then you encode it somehow magically in this, one vector, and then you output the other decoder, the output with and that's where the concept of encoder and decoder came from. And again, the reason I'm going through this, and I think history is important for that reason. If you, if you like you, and I should, yeah. So if you look at the current state of the art with transformers and all that, it almost sounds a little bit like magic. They have all these concepts, and how did they came up with, and then if you look at history, you'll see that all these concepts were already there. So the concept of encoder decoder was there from, again, recurring neural network for many years. Even the concept of attention was already there. So again, those of you that are trying to keep up with the AI, and there is this famous paper by Google, attention is all you need, which really introduced the transformer. For many people, again, that don't know history, that title doesn't make any sense, I think. But here is where that title is coming from. So attention, again, was introduced for recurrent neural networks. Because here is the problem when you have an encoder decoder with recurrent neural networks. Here at the output, you only have a vector. So it's very hard to encode a complex, sentence in just one vector. So, they came up with this idea that you can have the, the elements in the recurrent neural network on the encoder create this input to the decoder part through this attention. And again, here is an example of the attention mechanism for translation. So you have an English sentence here. The agreement on the European Economic Area was signed in August 1992. This is one sentence. And then you have another sentence in French. L'accord sur la zone économique européenne a été signé, and whatever. So you see that for the words that are, that have a simple, 1992, the attention says, this word comes from that word. On the other hand, there are some parts here, like, for example, European Economic Area, and, in French, the order is Zone Économique Européenne, and you see zone is with area, economic is with economic, and, so basically, and again, this attention mechanism was part of the backpropagation training. But again, this was introduced for recurrent neural networks. Basically, that's when Google came up with this, and it's already, 8 years ago, so time flies. But basically, they said, forget all that recurrent neural network stuff. That's really what that title means. That title means you don't really need the recurrent part because it doesn't really bring anything to the table. You just need this attention. And then you basically can replace these recurrent neural networks with this simpler, pattern of attention. And this is, again, quite powerful. And, that's how we got ChatGPT. Unfortunately, it's also very expensive. It has massive parallelism, as you can see. So, in some sense, it's worse than the fully connected layers because everything is connected to everything else. So you need a lot of computation to figure that out. But we are not going to talk in this class about transformers, really, but I wanted everyone to at least be somewhat, familiar and see this. This is, again, from that Attention is All You Need paper. It looks much more complicated than these, convolutional, well, I shouldn't say complicated. It's not more complicated. It's actually very simple because it's very repetitive. So, but it has concepts that kind of go beyond just, what we were talking at the beginning about, inputs and weights and neurons. In some sense here, it becomes more about, the matrices that we are talking about. But fundamentally, you have some inputs. There is an encoding. This is very important. It's an encoding part. This is called embedding, but you really encode those inputs into a very large multidimensional vector. And you need some encoding because, the words in a sentence have some position. But then you have these attention mechanisms, and these are the ones on the previous slide. So, and multi-head, I should also talk about multi-head. So multi-head is a way to do parallelism. So, so basically, you don't have just one attention network, you have multiple attention networks. And, quite a large number. And again, that gives different contexts to that the network can train. Also, this whole head can come as what does head mean? It doesn't mean this head. Actually, ironically, what it means, it's the head of a Turing machine. Again, if you go back to the previous slide, the first slide, when I was talking about Turing, the computer that Turing invented, so to speak, was just a concept. It was not a hardware thing. It was a tape, a computer tape. At the time, again, there were no hard disk drives. The memory was on a tape. And the head was the element that was reading the tape. So this multi-head really, in some sense, says multiple computers. There are some feed forward. So these are fully connected. So we still have those. And when you look at the computational effort for a modern transformer, a lot of the weights and a lot of the computation goes into these fully connected feed forward layers. And then you have some add and normalize. And at the end, you have this what's called softmax. So that's just a fancy name for winner take all in some sense. It's really, you can think of it as a soft one-hot encoding, which again is the cat in some sense, but there could be other things. We are not going to spend too much time on these, but I really need to mention them because we are talking about hardware. There is a parallel effort to everything that we talked until now into something that looks more like a biological, like our own, brain and neural system. And that's, that's called a spiking neural network because, again, instead of having numbers and things like that, you have these spikes. The network looks a lot like the other ones. You see, it's still neurons. And again, this tries to be much more biologically inspired, but the inputs and outputs are spikes. This is a difference, this is a fascinating thing where, the theory and the actual reality are at odds with each other. Theoretically, these should work because we have a proof of concept, a proof of existence in our own systems. Our systems work this way. They should also be very energy efficient. Again, there is a proof of existence. We only 20 watts in this brain here. No nuclear reactor needed. Yet we engineer, and that's another open problem for figure out a way to do this efficiently. And you may win a Nobel Prize because, again, there is a proof of existence. We exist and we work this way. If anyone figures out how to do an artificial system like that, that's going to be awesome. Okay, with this, I'm just going to say that there are many, many other things that we are not going to talk about in this class. And with this, we can take a break. Yes. Yeah, we still have 2 minutes for, well, 1 minute, yes.
You talked about when we use the recurrent neural network, you talked about the problem of the vanishing gradient. So let's say I have a neural network with 10 layers basically, and when I'm making some change at the input, you're basically saying it is getting vanished till the time it reaches the
10 is fine. 1,000.
1,000, yeah.
Oh, yeah.
So now, why not introduce a feedback from the first or second layer to the 800 or 900 layer so that the part which is vanishing out, it doesn't vanish at all?
Yeah. So I didn't get into the details. Some of those more complicated recurrent neural networks actually try to do that. So yes, people have looked at that, but that still doesn't solve the problem fundamentally. And yeah, I mean, yes, but they still don't work as well as the transformers because those have everything connected to everything. So yeah, you cannot beat that. Yeah. Okay. Thank you, guys. Thank you. So when are we coming back? Maybe let the people. Yeah.
Okay, so I think it's time for a lunch. So the lunch will be in front of the next building, in front of this building. So you can, like, my student will guide you where to go. And then we'll come back again. The next session will start at 2:30. So whether it will be theoretical or it will be the hands-on one. We are going to continue this one.
We can let's discuss.
Yeah,
the two
okay,
of us.
okay.
Yeah.
So we'll come